Hello?
Okay, so now let's move to the next talk. And now it's my pleasure to have here Alexander Dalzell, who is going to talk about random quantum circuits, transform local noise into global white noise. Okay, please.
All right, thank you. So this is joint work with my collaborators, Nick Hunter-Jones and Fernando Brandao. Both of them have been around this week. And the topic is noisy random quantum circuits. So for the first slide, I would like to, there we go. For the first slide, I want to set our convention for quantum circuits, for random quantum circuits, and for noisy random quantum circuits. So here's a typical quantum circuit diagram, which of course acts on n qubits with a series of two qubit unitaries and some single qubit unitaries as well. And then a measurement in the computational basis on all of the qubits, which yields an output from some probability distribution that we call P ideal, which is determined once you've specified what the unitaries will be. And when we say random quantum circuits, we mean that we'll choose each of these unitaries in the diagram to be independently random from some random ensemble. And in our work, we'll choose the Haar measure, although our results hold for any exact two design. And then once you've done that, you can define a concrete computational task called random circuit sampling, which is to, given as input a description of a circuit as above, produce a sample from this output distribution P ideal, and do so successfully for most instances, but potentially not every single randomly chosen instance. So now when we want to consider noise, we're trying to model local noise. So we'll kind of take that to its extreme and assume that the noise is only one local by inserting a single qubit noise channel after each of the two qubit gates on both of the qubits involved in the gate. And so for the analysis, we assume each of these noise channels is identical, but this is sort of not essential to the overall point. We define this parameter epsilon to capture the noise strength of these noise channels, which for a Pauli error channel would be the probability of having a Pauli error occur at that location. So once you've added these noise channels, the output of your circuit will be different. It might be a mixed state, whereas previously it would have been a pure state. But you can still measure it in the computational basis and obtain a sample from some other distribution that we call P noisy. So it's important here to look at these two distributions, P ideal and P noisy, which correspond to the same circuit, the only difference being the insertion of these noise channels. So this is sort of meant to capture the essence of what's going on in recent experiments on actual devices aimed at achieving this goal of quantum computational supremacy, which is the goal of doing a concrete computational task on your quantum device that could not have been also performed on a classical device, at least in any reasonable amount of time. So Google performed an experiment in 2019 on a 53 qubit system arranged in a 2D lattice, where they ran circuits of about 400 gates, where the error rate, if you try to kind of translate it into the model from the previous slide, corresponds to about 0.5% at each of those noise locations. So this may seem like a small error rate, but when you total up the overall probability that there were no errors over the course of the entire computation, you end up with a very small number. In their case, it was about 0.2%. And then just last year, there was a larger version of this experiment performed at the University of Science and Technology of China on 60 qubits and nearly 600 gates. And due to the fact that the circuit size was larger, there's just more error channels, the overall fidelity, we're calling this kind of probability of no errors, the fidelity, is 0.04%. So these are very small numbers, and it's really important to kind of take in how small they are, and the fact that we would have to repeat the experiment 1,000 times and only expect one or two of our experimental runs to have happened without an error. So we would still like to be able to say that despite this low fidelity and despite having lots of errors, we're still doing something similar to what the ideal computation would have done. So the kind of goal here, the most you could hope for is that the total variation distance between the two distributions would have been small. Here, the total variation distance is sort of the natural way of measuring the distance between two probability distributions. And when you have a system like the one we're studying with S error locations or order S error locations and then epsilon error probability at each location, you would expect the total variation distance to go linearly in the product of those things, kind of the total expected number of errors. But in the case of the Google and USTC experiments, this is a large number. So in the case of Google, I think you would expect on average 6 errors, which would tell you that the total variation distance is actually not small at all. It's probably close to its maximum. So this is not really a good way of saying that the noisy device is actually doing something similar to the ideal device. So the way that one might try to get around this and say that nonetheless the noisy device is doing something similar to the ideal is to make this white noise approximation, where you say that the noisy output distribution is roughly equal to, with probability f, an output from the ideal distribution, and then with probability 1 minus f, just a completely uniform random output. This is what we mean by white noise, this kind of randomness, the fact that there's some probability of an error, and when there is an error, it can just be global white noise. They did give some weak numerical evidence in one of the papers leading up to their quantum computational supremacy experiment, where they looked at the left-hand side of this approximation numerically for system size up to about 20, and showed that it was consistent with the behavior you would expect from the right-hand side. But they didn't really go so far as to compute the error between the left-hand side and the right-hand side, which later when we talk about implications, we'll discuss why it's really important that this approximation is very close if you want to actually use it in practice. And the reason that they wanted this to be true, there's perhaps 2 kind of ways you could motivate it. The first thing is that if you do know that your output distribution has this form, then it immediately justifies using the linear cost entropy benchmark to try to numerically figure out what the value of f is and kind of characterize the amount of noise in your device. Now, I won't say, so there are other forms, you don't have to have this approximation to be true in order for the linear cost entropy to be meaningful, but if you do know that, then you definitely know that it's meaningful. And then the second reason, which is I think more important and sort of the motivation of this work, is to try to give a more strong argument that the task being performed on the device is actually hard for a classical computer. We'll come back to that later. So what do we show? We are able to give an upper bound on the amount of error in this approximation. So here we have this white noise distribution, this combination of the ideal and the uniform. And we have the parameter f, which is decaying exponentially in the number of expected errors. And then what we do is we show we compute the total variation distance between these 2 distributions, and we take the expectation over choosing our unitaries to be each of the components to be hard random. And we show that this is upper bounded by the product of 2 small numbers. The first one is this f, which is decaying exponentially, and the second one is growing with the error rate epsilon and the square root of the number of error locations in the device. So I made this animation to kind of give another picture of what's going on, and of course these probability distributions are high-dimensional objects, so we shouldn't take it too seriously to put them on this 2D plane. But I've tried to do so nonetheless. Here I'm putting the uniform distribution at the center of this circle, the ideal distribution at the north pole of the circle, and then I'm going to imagine starting with an ideal circuit and adding in noise locations and seeing what happens to the noisy distribution. So 2 things are going to happen. The first thing is you're going to get a decay toward the uniform distribution, the decay of the fidelity. This is going to be represented by the arrow getting shorter. And secondly, the direction of the arrow is going to stay mostly pointed in the direction of the ideal distribution. So if you play it, you see that the fidelity decays, but the direction of the signal is still kind of uncorrupted. If you were to subtract out the uniform distribution and then renormalize your distribution by dividing by f, you would have something that was mostly in the same direction as the ideal. But it's not exactly in that direction, and we can kind of model the deviation in the direction as sort of growing like the square root of s, which is reminiscent of the way an unbiased random walk might grow from its origin. So that's how we modeled it for the purposes of the animation. So what are the caveats? The biggest caveat is that there's a noise threshold in order for our results to apply. So in order for our theoretical proofs to apply, we need an assumption that epsilon is much smaller than 1 over n log n, which might be small in practice. It's important that it's independent of the circuit size s, but we do believe it can be relaxed to epsilon smaller than order 1 over n, where the constant prefactor there is not too unreasonably small, maybe about like 0.3 or something like that. We've done some numerics on it. But we believe that this is a fundamental requirement for the white noise phenomenon to occur, and that actually if you're above this threshold, then the white noise approximation might just be false. I'll also mention this is one distinguishing feature between this talk and the next talk, where they look at similar things, but they're looking at a different regime where epsilon is not so small. So all of the results are in perfect agreement. And then there's an additional requirement that the circuit size has to be at least n log n, which isn't too much of a requirement. It means that the depth has to be about log n, but it does rule out the case of constant depth circuits. And then finally, in our proofs, in order to for them to fully apply, we need the connectivity of the random quantum circuit to be either complete graph, where you have all-to-all couplings, or one dimension where you put the qubits on a 1D ring and you do nearest neighbor gates. But we don't think this is essential. Under a weak conjecture that like 2D circuits have this anti-concentration condition after only log depth, then our results would also apply in 2D. So we think it's really a generic phenomenon. Okay, so now that I've explained the result, I want to talk about a couple of implications. So the first implication is just a general sense that if you have this white noise approximation, then you can extract the signal from your experiment by repeating it many times. And one concrete instance where this would be substantiated is when you have some function f of x, where x is a classical bit string, and then you want to take samples from an ideal quantum computation and compute the mean of f of x when x is chosen to be the output of that quantum circuit. So this is often the case in, for example, like the QAOA algorithm, where you have some classical cost function you want to compute its average of. And if we want to compute this mean mu, but we only have access to a noisy device, then we can leverage the fact that let's say we know that the white noise approximation is exactly true. Then we would still be able to estimate mu by repeating the experiment many times and just dividing the average we get by f. To do this, we would, if we wanted to get an estimate to precision delta, we would need order 1 over delta squared times 1 over f squared samples. So we are paying a high overhead in the number of repetitions that we would need to do, order 1 over f squared. But in the near term, this might be advantageous compared to doing error correction. Right, so QAOA is an example potentially, although we don't know if this white noise approximation holds in that case because we're only really examining random quantum circuits. Okay, and then the other implication is related back to this argument for quantum computational supremacy. The goal here, of course, for this, if you're trying to show that this advantage exists, you need to do two things. You need to have a concrete task that you can say your device actually accomplished. That's number one. And then number two, you need to have an argument that the same task would have been difficult to do on a classical computer. So we're going to be able to kind of provide both for these low fidelity experiments. And we start by looking at prior literature. So prior literature had examined this approximate RCS task, where the task is to sample from a distribution that's close to the ideal in total variation distance, right? This total variation distance should be less than or equal to delta. But as we previously explained, this requires epsilon times s to be a small number, which is not the case in actual devices we have today. So what we propose is a different task, which we call white noise RCS, which is to sample from a distribution that's close to the white noise distribution. And how close does it have to be? It has to be at most f times a small number close. And what our work does is it shows that actually, yes, if a device is well modeled by the noise model we showed on the first slide, then this task can be accomplished as long as epsilon times square root s is a small number and epsilon is beneath this threshold. And of course, here you can see the contrast that epsilon times square root s, it's much easier to make this a small number than epsilon times s. So on the next slide, we're going to try to examine whether the actual device satisfies this assumption or not. But yeah, so in theory, this kind of justifies trying to perform an experiment like this based on the white noise RCS task at low fidelity. What's more, we can give a reduction between these two tasks and show that they're essentially equivalent in a concrete complexity theoretic sense. If f is only polynomially small, then in fact, one of these tasks is hard for the polynomial hierarchy if and only if the other one is. This is sort of the gold standard for what makes a hard classical task in this line of work. Now, if f is exponentially small, you can't say something concrete about the polynomial hierarchy, but you can still assert that that white noise RCS is kind of at most a factor of f easier for the classical computer than the approximate RCS task. So this immediately means that we can kind of import all of the evidence that we had that approximate RCS was a hard task over to white noise RCS. Now, you might question some of that evidence because there's still conjectures as to whether approximate RCS is hard, but at least this puts white noise RCS on almost as good footing as approximate RCS for this purpose. So now I want to, So now I want to kind of evaluate whether these epsilon square root s and epsilon less than order 1 over n conditions are actually true in the experiments. And we won't be able to get a definitive answer. And the main reason we won't is because they had the 2D layout, which we can't simulate exactly. There's other kind of simplifications we made in our model that make it not directly relevant. But nonetheless, what we can do is we can imagine that instead of a 2D architecture, we had a complete graph architecture. And then we can exploit a certain symmetry to actually numerically evaluate our upper bound on the total variation distance divided by f. So this is the thing on the y-axis that we want to be a small number to be able to say that the white noise approximation is meaningful. So here we plugged in the values of n and epsilon for these two experiments and plotting it as a function of circuit size. And there's sort of both good news and bad news. The good news is that the error rates achieved on the actual device appear to be beneath this threshold because at large circuit size, it approaches this behavior that we were expecting theoretically of f times epsilon times square root s. And even for like circuits of very large size, thousands of gates, we still have an approximation up to like 0.2 or something, which is not tiny, but it's like meaningfully small, at least in some sense. And then the bad news, I guess, is that if you plug in the actual circuit sizes, you're kind of in this initial regime where you haven't quite scrambled enough yet to be able to apply the techniques, or to be able to like make this assertion. So it sort of means that we would have more evidence that this white noise approximation we're holding if we actually performed a larger depth circuit at the exact same error rate. Of course, this would come at the expense of smaller fidelity. But yes, so there's caveats here, including the fact that we're not doing the 2D architecture. It's also an upper bound and not a lower bound. We don't really know quite how to get a lower bound on this. And then also, this is the average, and we don't know what the typical would necessarily look like. Okay, so in this slide, I just want to give a one-slide overview of how we do the proof and kind of give a plug for the method that we use. So the idea is that we have this total radiation distance quantity, which is inherently a one-norm quantity. And we want to express it in terms of two norms. So we kind of just do a standard one norm to two norm bound, and we have these 3 second moment quantities in the random quantum circuit. Z0 is the ideal squares. You have 2 copies of the ideal, then you have 1 copy of ideal, 1 copy of noisy, and then you have 2 copies of the noisy distribution. So this is like kind of an easy kind of first step. But then the crux of the proof is to map these second moment quantities to the expectation value of a certain random walk on bit strings of length n. And then the third step is to kind of analyze this random walk and prove tight bounds on the expectation value. And this is kind of, I think if you can express a random quantum circuit problem in terms of the second moment, this is like likely to be an effective method in general. So if you're interested, you should look into it. And I want to conclude with just a perspective on this result and dealing with errors in the near term and far term. So in the long term, we want to do quantum error correction, which operates by, when an error pops up in your circuit, you want to kind of make sure it doesn't propagate, because you want to identify which error happened and be able to correct it in an organized way. And the cost here is more qubits and more gates. And what our work suggests is that there's a potentially alternative strategy for the near term, which is to simply not let the errors scramble completely, and then try to just treat the noise as complete global white noise. And in some applications, this is nice because the signal of the ideal computation can be extracted just by repeating the experiment. Of course, this begs the question, we show that for in the average case, when you choose these gates randomly, this approximation does hold. But often we're interested in very specific circuits that may fall into some corner of the space where this approximation is not actually true. So it'd be nice to kind of give evidence that it's true in other interesting situations as well. Okay, and that concludes my talk. Thank you for your attention.
So thank you very much, Alexander, for this very clear talk. Do you have any questions?
Hey, thanks for a nice talk. Maybe I missed this, but does your kind of proof depend on noise being gate independent?
Does it what? Sorry?
Does it depend on noise being gate independent? And
Yes.
How does it change if?
Yes. So our proof works for any single qubit noise channel that's independent of the gate. And we analyze like general noise channels as long as they're unital. And we find that this white noise approximation is good as long as the noise is mostly incoherent. So actually it doesn't work for coherent noise. But you can plug it into our bounds and you get really bad bounds.
Okay.
But it has to be gate independent, yes.
Okay. So you'd expect you wouldn't be able to sort of extend this to more general types of noise?
Yeah, I think it's important that the gate independence is definitely important because the technique involves averaging over the gates and the noise separately. So if you had some correlation between the gates and the noise, you wouldn't be able to do that, and kind of the technique would break down here. At the step two would just not. Step two would just not work. But it's certainly interesting to think about that as well.
Okay, thank you.
Yeah.
Thanks for a great talk. Do you have any ideas on how you might accelerate the process of scrambling of these errors in a regime where the depth is not long enough?
Yeah, I guess there is kind of a way of viewing this as sort of like the reason that there's some error in the approximation is because you can have like distinct configurations of errors that are secretly the same configuration because the random circuit kind of maps one to the other under propagation. So maybe if somehow you chose your circuit to like make these collisions very rare, you could make it work. But I mean, really the reason, if you look at this, like the reason that the blue line decays like more slowly than the red line is not because the errors are scrambling more slowly, it's because the fidelity is decaying faster. Right. And we've normalized by fidelity here. So that's sort of the thing you're racing against. I'm not sure if you can really accelerate it that much, but yeah, maybe you could a little. Yeah.
Thank you.
Sorry, I don't know.
Online, Ian Lim asks, in this work you use total variation distance. Do you think similar bounds could be established for something like a KL divergence?
I think you would need a version of step one that changes the KL divergence into some sort of two norm quantity. I'm a little skeptical. I haven't tried it just because I feel like the KL divergence is a bit sensitive to extremely small error probability, output probabilities, which might make the statement not true also. But it would be interesting to try it. The problem would be step one.
Cool. So thanks a lot. Let's thank the speaker again.